So today we are going to do a full course on greedy algorithms and we are going to learn everything there is to know. We are also going to solve 10 most asked, most popular greedy problems, and I can guarantee you that by the end of this course, you would become a complete pro on all sorts of greedy questions. You would be able to identify, understand and solve them flawlessly. So without any delay, let's get started with the course. So greedy algorithm is nothing but a problem solving technique where you take the given problem and try to carve out the biggest possible solution you can, and then try to deal with the remaining portion, and also again repeat the same problem, and even with the remaining portion of the problem you also try to carve out the biggest solution that you can, and so on and so forth. So you basically break a problem down into sub problems, and then even in the sub problems you also repeat the same approach, but at every given chance you are trying to find your best way to solve as much of a problem as you can. Let's try to understand this with an example. Suppose you are a cashier at one of the gas station and you realize that someone comes to you with $100 bill who only had the amount that you need to charge was $67.35. Let's say that this was their bill and they hand you over $100. What is going to be your first approach? The immediate thing that would come to your mind is that you need to return $22.65 to that person. Now if you have to return $22.65, the first thing you are going to do is take out the biggest chunk by the biggest denomination of money. So you are going to take a $20 bill, which means now the remaining amount is going to be $2.65. Once again, for this one you are also going to repeat the same problem and same approach. So you are going to take a $2 coin, and yes, in Canada we have $2 coins, so we can use that, or a $2 bill, and then now you only have to deal with 65 cents. And for 65 cents, once again you are going to take 2 quarters, so that is going to be 50 cents. And now for the remaining 15 cents you can take 1 dime, so 10 cents, and 1 nickel, so that is 5 cents. And overall, with this denomination you would have created basically the ideal amount of money that you will have to return to that particular person, and you can just hand them over. This is where you took the biggest problem, that is that you need to return to $22.65, and then you started breaking this down into the subsequent portion of the different denominations that you could, and at every given step you were being greedy and you were trying to solve the most amount of problem at any given point. And that's the whole approach on solving greedy problem. Now, if you see the structure of the greedy problem, it looks very similar to a lot of other approaches that we have seen. Number one, it seems very similar to dynamic programming approach. Second thing, it seems very similar to recursive approaches that we see, because we are dealing with solving sub problem within a sub problem within a sub problem for different inputs. And third thing is, many times you can also consider it closely related with most simple brute force approach. And you would be true in saying that greedy approach looks very similar to all of these three techniques, but there are slight variations and differences. First, let's understand that what is going to be the difference between a greedy approach and a dynamic programming approach. Well, for the greedy approach, you are trying to solve the biggest chunk of the problem. That's it. But in the dynamic programming approach, you actually take a problem and you break the problem in sub pieces, and for those sub pieces you try to store their answer, and based on that stored result you try to build more sub pieces, and then you build your solution. So if we have to consider greedy approach, you can treat it as if eating a cake, where you have a big cake, you take out a big chunk of the cake, so now you are only dealing with a smaller sub portion of the cake, and once again you can take out the biggest chunk, and now you are only dealing with even smaller sub portion of that cake. But meanwhile, in a dynamic programming, you can treat it as building bunch of different Lego bricks, and based on the combination of having these Lego bricks, you would be able to combine them together to build your solution in a particular fashion on top of already computed results. So this is the visual difference between a greedy approach and a dynamic programming approach. And you would see in many problems where you would feel like, hey, this should be solved using greedy approach, but eventually you would hit a brick wall, and you would find that dynamic programming would be much better way, and vice versa. So you would always be using these two tandemly, interchangeably, and you can make that judgment call that what do I need to choose, a greedy approach or dynamic programming approach. Next thing is that what is the key characteristics to understand that this is a good suitable candidate for a greedy problem solution. Number one thing is it should have an optimal substructure. So what do I mean by optimal substructure? Well, because originally you are trying to solve a bigger problem, and you are taking some or majority of the portion out of that problem, and now you are only trying to solve a smaller problem, and once again repeating the same process, so on and so forth. So this is a good candidate to understand that, hey, can I apply greedy solution to this? Let's go back to our question of the cashier who was trying to break money, because originally the cashier had a bigger amount that needed to be returned, and then after taking a big chunk out of it, $20, we still had a smaller amount that would still needed to be returned, and we would apply the same logic on top of it. So that is number one. Number two thing is, whenever you are trying to deal with maximizing or benefiting from your input, so let's say that I give you an example. Let's say even in the cashier's problem, I would have told you that you need to return the change in the minimum possible bills or coins, and that minimum word would be a key characteristics or a key phrase for you to understand that, hey, let me try to solve this problem using greedy approach. So whenever you are trying to maximize your profit or minimize the amount of work that you have to do, or there is the greatest value that you are trying to find or the lowest value that you are trying to achieve, some keywords like this, if whenever you see something like this, always think that, can I use greedy approach to solve this problem? And more likely than not, you would be able to do it. Like if you see a very popular example, we have a very famous algorithm called Prim's minimum spanning algorithm, and I have done a separate video on this, and you can find it at any different place. But this algorithm typically uses the greedy approach, where if you are trying to traverse between any two particular node at any given moment, all you need to do is you need to pick the direction which leads the smallest edge weight, and if you keep on doing that, basically you would be able to traverse the entire tree in the minimum spanning or with minimum cost. And that's a great example on how this very popular and very famous tree and graph related algorithm can use greedy algorithm technique to basically exist. So there are many benefits of using greedy algorithms, and we are going to see about everything about all of them in the top 10 LeetCode problems that we are going to solve. So now, without any delay, I won't spend much time explaining the theory. I would rather explain you these 10 problems, and you would be able to understand that what different problems can be asked, what are the pattern that we are trying to recognize over here, and how do they actually work. So without any delay, let's get started with these questions now. The LeetCode problem we are going to solve now is called assign cookies, and we can see that this one is the LeetCode easy problem, and also this is a very popular problem. The problem statement is quite straightforward, that we are an awesome parents who wants to give cookies to our kids. But the thing is, every single child that we have has a different preference on the size of the cookie, which means that at any given factor we can only give them one cookie, but on top of it we are given two arrays. First array is that what is the preference or greed of the child, so that is given by the array called G, and we are also given the total size of cookies that we have, and that is given by S. Now at any given moment we can only feed the child if the size of the cookie is going to be greater than the greed of the child, like greater than or equal to. So let's try to understand this with an example. Suppose we currently have 3 children, so and for each of the child we have different greeds. So let's say that the first child is okay with 1, second child is with 2, and third child with 3. And currently we only have 2 cookies, and the size of both cookies are just 1. Now in this case we can see that for this child 1, because that child has just greed of 1, you can feed a cookie of size 1, so that's fine. But for this child 2, the child 2 has a greed of 2, but we only have the remaining cookie with just one size, which means we cannot feed this child, or neither we can feed this child. So in this case we need to return 1, because we are only satisfying the greed of just one child. So this is the whole problem statement. Let's just learn one more example. Suppose the given greed is equal to 3 and 4, and the given size of the cookies are going to be 1, 2, 3, 4 and 5. So in this case we can see that we have bunch of different cookies, and we also have cookies of size 3 and 4, which means we can satisfy both the kids. So we need to return 2 as the answer, because we are satisfying 2 kids. So this is the whole approach of the problem. Now let's see that what is going to be the brute force approach. Well, brute force approach is quite straightforward. For given input based on the size and the given cookie size, for every single greed we can try to iterate over the given sizes array and see that if the cookie of that particular size exists or not. If it exists, then we can simply return true, or we can just say that we can fulfill the need of that child. If it does not exist, then we can simply return the other way around. Now this approach would work as expected, but the thing is this is going to go into big O of n square time complexity, because for every single greed we will have to look into the sizes array or vice versa. A better approach is that we can actually sort both the given input for greed and also for the sizes, and then we will only have the greed from smallest to the largest. So let's say that we can have an input like this, and we can have a sizes also ranging from smallest to largest. Let's say something like this. In this case we will just need to do the matching of 1 to 1 between both of them, and for any particular value of s of I, we need to check that if that value is greater than or equal to the current greed of that child. If that is the case, then we can say that we satisfied that child, so we can update the counter and move on to the next child, and also we can move on to the next cookie. If that is not the case and we identified some scenario where let's say that the given size is actually lesser than the child we are trying to satisfy, so let's say the child is 1 and the cookie size is 3, in this case we will still remain at the same child, but we will update the cookie size, or go to the next counter in the cookie. So in either case we are always going to be updating the cookie counter, but we would not update the child counter if this condition does not satisfy. In the end we only exit out of the loop in two conditions. The first condition is that either we run out of the greedy children or kids, or second condition, we run out of the total number of cookies. In either case we simply check that where do we land in terms of child index, and that is going to be our answer. So this approach would work perfectly fine, and it is an acceptable solution in an interview that you can expect and solve so far. Now in the coding part, I'm going to show you the code for this approach because this is a simpler approach, but we can also have a better approach where we can use a hash map to basically go over the frequency of cookies based on the given sizes array. So what we can do is we can have a size array, then we can iterate over all of the different sizes, so let's say 2 and 3. Then we can have a hash map. So inside the hash map we are going to add all of these sizes and their frequency. So currently we have a cookie of size 2 that is occurring once, and then we have a cookie of size 3 that is also occurring once, and now we will try to satisfy the kids. So the idea would be that let's say that we are currently at child number 1, and the greed of this child is also 1. So we are going to go to our hash map and we will try to see that whether any cookies with value 1 exist. If it does not exist, we will also check for any cookie with value 2 exists, so on and so forth, as long as we find some value inside the hash map. So we identify that yeah, there exists a cookie of size 2. So because it exists, we are going to reduce the frequency, so this would become 0, and if this becomes 0, we can delete it from here, and we can say that this child that we had was also satisfied. And now we will move on to the next child that has the cookie preference of 2, and once again we find out the size and we are going to reduce the counter, and if our hash map becomes empty, then we can simply return the child counter. Or if our let's say instead of that, if our like number of greedy kids becomes empty, then also we can return the child index. So this is a better optimal approach, but the thing is this solution is not quite straightforward, and also it yields big O of n space complexity. So whenever you give this solution, your interviewers are going to say that what if I don't want to use extra space? In that case, you will once again come back to the sorting solution. So let me just give you side by side comparison. For sorting, the time complexity is going to be big O of n log n, but the space complexity is also going to be big O of n log n, and this is to run the sorting algorithm. For the hash map approach, the time complexity is going to be big O of n, which is faster, but the space complexity is also going to be big O of n, which is greater. So you can pick and choose your solution, and also let me in the comments if you want to see coding for both approaches as well. Currently, I'm only going to show you the coding for the sorting approach. The coding solution is quite straightforward. First, we are going to use the inbuilt method to sort both the kids array and the sizes array. Then we are going to have two variables to store the value of the current child index that we are iterating over and the current cookie index that we are iterating over. Next, the simple thing is, while either the length of child index is less than the length of the given grid, or the length of cookie index is less than the given total number of cookies, we simply need to check that if for the given current size index, if the size of the cookie is greater than the grid of the child, then we need to update the child index and move on to the next child, because we already satisfied the current child. If that is not the case, basically we need to go to the next cookie in either case. And eventually in the end, we simply need to return the total number of child index, which means the total number of kids who got satisfied with the size of the cookie that they received. So this is an awesome solution. Let's try to run the code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs beautifully and beats good chunk of other solutions, which is pretty awesome. Now I know that there are ways to make this even faster, and we can use some other technique apart from using the n log n sorting techniques, but anyways, this is still a good solution. So the LeetCode problem we are going to solve now is called valid parentheses string. We can see that this one is a LeetCode medium problem and also a very well-liked problem. Basically, we are given a string S that contains only three types of characters: open parentheses, closed parentheses, and a star. Now we need to return true if the given string is valid, and there are some definitions given on what is valid. Basically, any left parentheses must have a corresponding right parentheses. That's fair. Same way, any right parentheses must have a corresponding left parentheses. Next point is that left parentheses means opening parentheses must go before the corresponding closing parentheses. So this is valid, but if we have like this, then this is not valid. Okay. And last one is that if we are given star at any moment, then we can consider star to be whatever we want. So we can treat it as a right parentheses or a closing parentheses or an open parentheses, or we can also consider it as an empty string, so that makes no difference. So let's try to see some examples. Suppose we are given a parentheses like this one is a valid. If we are given a parentheses like this, once again this is a valid. If we are given a parentheses that contains star, once again this is a valid. In this case, we are treating the star to be an empty string, which means we are basically left with this. We can also say that this is also a valid string, and so on and so forth. So the only scenarios where it is not valid is if we are dealing with number of like out of order parentheses, or we are dealing with multiple parentheses of being like this and only one parentheses like this. So this is also not valid. So let's try to understand the most common logic on how we can pursue solving this problem. Now we know that if we are only dealing with working with problems that only contains parentheses, we can simply use a stack and solve this problem very easily, very efficiently. There are like a lot of different examples of that. I would not go in depth in this case, because the important thing for this problem is this asterisk. So whenever we are dealing with an asterisk, we have three possibilities. We can either consider it to be an open parentheses, we can consider it to be an empty string, or we can consider it to be a closed parentheses. So in each of the cases, let's say that if we are dealing with multiple stars, there can be many possible combinations and permutations that we should be able to make. But that adds more and more complexity to our problem, because let's say that we are given a string like this. Now in this case, we need to basically have option over here to choose 3 different entries for each 3 different options we have another way to choose 3 more different options, and so on and so forth. So we can make many different possible combinations. So we'll have to do things smartly. So one solution I'm suggesting in this case is that we use greedy approach, and basically we iterate over the given input in just a single fashion, and we keep track of the number of open parentheses, and we also define that what is the maximum number of open parentheses that we currently can have depending on the star value, and what is going to be the minimum number of open parentheses we can have depending on the given star value. Now there are two possibilities. One possibility is that for any particular star, if we treat it as an open parentheses, which means there is one more open parentheses left for us to deal with. So in that case, we can add basically that value to the max pair character, or we can treat the star as an empty string or a close parentheses. In this case, we have one less open parentheses that we need to deal with. So in this case, we would update the value for the minimum character. So let me just walk you through the solution I'm suggesting. Let's say that we are currently given an input like this. So in this case, we are going to simply have a few rules for two variables that I'm suggesting. First variable, the variable's name is maximum open, okay? And second one is minimum open. Now for each of this, we are keeping track that what are the maximum number of untouched open parentheses we have and what is the minimum number of untouched open parentheses we have. The logic is quite straightforward. We are simply going to follow few rules. If the given input character is an open parentheses, then we will have to increment at both the places. So we are going to increment at max and min. If it is a close parentheses, which means there is one less open parentheses for us to deal with. So in this case, we would decrement at both minimum open and maximum open variables. And we are going to initialize these with value 0. And if the given value is star, in this case, we have two possibilities. So there is one possibility, we treat this as an open parentheses, or we treat this as an close parentheses or an empty string. So if we are treating it as an open parentheses, which means there is one more open parentheses left for us to check. So we are going to increment at our max open. So for max open, we are going to update the value whenever we encounter a star. And whenever we encounter a star, we can also treat it as a closing bracket. So we will decrement the value at the minimum variable that we have stored. And these are the rules that we are going to follow. Now, there are a couple of conditions that would allow us to solve this problem. Basically, find the loose cases. So first case is that if at any given point we identify that given number of maximum open parentheses go into negative, which means that there are too few open parentheses and too many unopened parentheses, because remember when this can go into negative, whenever we have a closed parentheses, then we decrement the value. So let's say that if for the given example, if the first character in itself is a closed parentheses, then we would have decremented the value for maximum open and minimum open. So in this case, the maximum open would have become negative. So we can say that now, even if this is like the most valid string, this is always going to be not valid because it has an open parentheses where we don't have a corresponding closed parentheses. So this is one scenario that we can keep track of. Second scenario is that at the end, our goal is to ensure that there are no untouched or there are no left open parentheses. So let's say that we iterate over the entire given input using these three rules, and we find that there are no open parentheses, which means the min open is 0, then we can simply return 0 as the answer. Now next thing is we have a possibility where if we are encountering a star, we are basically reducing the value of the min parameter. So min parameter can still go into negative, but the thing is this would not directly say that we are dealing with an invalid string. So in this case, if for some reason the minimum variable goes negative, then we are simply going to just start it back to 0, treating that there are no open parentheses left for us to check. And I know that there are a lot of rules that I just talked about, but the thing is, if you just understood what we are trying to do with the example, then it would make perfect sense. So let's say that this is our minimum variable, this is going to be our maximum variable, and we are going to start iterating in this fashion. So first we identify an open parentheses, which means we are going to increment the value for both in min and max. So currently both values are going to be 1. Once again open parentheses, so both values are going to be 2, and once again open parentheses, both values are going to be 3. Now notice what these values define is that what is the minimum number of open parentheses that we will have to deal with, and what is the maximum number of open parentheses that we have to deal with. So far we haven't encountered any star, so that's why the numbers are same amongst both of them. Now we encountered a star, so we can treat the star as either an open parentheses or a dot or a close parentheses. If it's a one more open parentheses, then we would have 4 open parentheses that we will need to deal with. And if we treat this as a closed parentheses, then we will only have to basically deal with one less open parentheses, because we can basically close these two parentheses. So in this case this value would become 2, and let's try to see this by different examples. So first 3 values we have as open, then we have a star over here. So what are the two possibilities? First possibility is that we create a close parentheses. So in this case this becomes a close parentheses. So how many number of open parentheses that we are left to deal with? 2, which we are representing over here. If we treat this as an open parentheses, in this case how many number of maximum open parentheses that we will have to deal with? 4, and that we are capturing over here. And this is the whole logic of the entire solution. So now let's continue moving forward. So once again we identified one more star. So once again the minimum variable is going to be decreased by 1, so this would become 1, and maximum variable would be increased by 1, so this would become 5. And now we encounter a closing parenthesis. So whenever we encounter a closing parenthesis, basically we are reducing the values at both minimum and maximum values. So this would become 0 and this would become 4. Now because we reach to the end of the loop, we don't care about this maximum variable. This maximum variable is only there to keep track of if this goes into negative or not. If it does goes into the negative, which means we can stop immediately and return false. If that is not the case, we check the value of this minimum variable, and if because this is 0, so in this case we can return true for this one, and that this is a valid string. So this is the whole idea behind the solution. Now if we see time and space complexity, time complexity is going to be big O of n because it's quite straightforward. Space complexity is going to be big O of 1 because apart from using couple of variables, we are not using any extra space. So this is a wonderful solution. And now let's quickly see the coding solution for this one. So the coding solution is quite straightforward. First, we are going to initialize a couple of variables called minimum open and maximum open. This is to keep track of the minimum possible open parentheses and maximum possible open parentheses. Now we are going to start iterating over character by character inside our given input string s. And for every single character, we are going to check that if there is an open parenthesis, then we need to increment both min open and max open. Otherwise, if it is a closing parentheses, then we need to decrement both min open and max open. And if that is not the case, which means we have identified a star value, in this case we will need to decrement the minimum open because we are treating it as a closing bracket or an empty string, or we need to increment the maximum open because we are treating it as open left parentheses. Now at any given moment we realize that the max open is less than 0, which means we can return false immediately because there are just way too many closing parentheses compared to the subsequent open parentheses. Now if that is not the case, then we are going to check that at any given point if the min open becomes negative, then we are simply going to initialize the value starting from 0. So min open can go into negative, but we don't care about that. Now in the end we simply need to check that if the given min open is equal to 0, which means that there are no minimum possible left open parentheses. So in this case we can return true, saying that the given parentheses string is valid. So let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And code beats 100% of all the other solutions, which is exceptional. So once again I would be posting this solution in the GitHub repository that we have created, so you can find it from there. Thank you. The LeetCode problem we are going to solve now is called gas station, and we can see that this one is a LeetCode medium problem and also a very well-liked problem. The statement is quite straightforward that there are n gas stations along a circular route where the amount of gas at any particular station is defined in the array gas fi, and then we are told that we have a car with unlimited gas tank that cost of I gas to travel from ith station to the next I plus 1 station. Let's do a quick recap. Basically we are given two arrays. First array is called gas and second array is called cost. Basically gas, any particular value inside the gas array defines how much oil or how much gas we can fill in the tank at that particular location. Cost at that station defines that if we have to move to the next stop, what is going to be the cost in terms of gas amount. So based on distance, you can understand it that way. Now we begin our journey with an empty tank at one of the gas stations. Okay, now we have basically need to make sure that given these two arrays, we can start from any particular gas station's index, and we need to check that if from that gas station's index are we able to travel around the entire circuit once in a clockwise direction. If that is the case, then we need to return the location of that index. If that is not the case, we need to return -1, and we are guaranteed that we would be able to find a solution. So if there exists a station, there has to be only one station that can fulfill that property, otherwise it would be -1. There would not be any duplicated answers. So let's try to understand this with an example. Currently we are given a variable called gas and we are also given variable called cost. At any particular index position, this is the amount of gas we can fill in the tank, but if we need to go to the next stop, then this is going to be the cost associated with that, and so on and so forth. So let's try to see that what would be the answer in this case. Let's say that suppose we start our journey from index position 0, which means currently our car has so let's just mention that what is going to be the tank amount of gas in the tank. Okay, so currently tank has empty, so no gas at all. At position number 1, we would be able to fill in one amount of gas. So currently tank has only one amount of gas. Now let's say that if we need to reach to next position, index position number 1, then we will have to pay this cost. If we were to pay this cost, it would be 1 minus 3. So basically our tank would go in negative, so we would not be able to reach to this position number 2 from tank number 1. So we can clearly say that option 0, it does not work. Same way we can also check that from option number 1, currently our tank would be initially 0. Okay, let's just repeat the calculation. So this is going to be 0, but now we can fill in plus 2, so now the gas would be 2. But if we have to get to option number 3, then we would have to spend 4 units or 4 liters of gas, which means 2 minus 4 would become -2. Once again, we would not be able to reach to item number 4, so that would also not work. So let's just start our iteration from this third index position. Once again repeating the same logic. Currently tank is going to be 0, but we can add tank as 3, so 3. And but if we have to reach to next station, the cost is 5, so 3 minus 5, once again this would also not work. So now we are at this index position number 3. So currently our tank is going to be 0, so we can add value number 4. So now tank has 4 liters of gas. If we have to reach to value number 5, then we need to spend 1 liter of gas. So once again this is also going to be 4 minus 1. So basically when we reach to this index position number 5, our tank would have 3 units of gas. Once again at this position we would fill in 5 units of gas, so this is going to be 3 plus 5. But now from this, in the clockwise direction, basically we will need to reach to station number 1, but we will have to pay cost of 2, so 3 plus 5 minus 2. So overall this is going to become once again 6. So we are going to have 6 units of gas when we reach to this position number 1. Once again over here we will add 1 unit of gas, but in order to reach to next element we will have to spend 3 units of gas. So now when we reach to this index position number 2, our gas is going to be 6 plus 1 minus 3, so 7 minus 3, so basically this is going to be 4. Once again from this position number 2, we need to reach to position number 3. So 4 plus 2 minus, we will have to spend 4 units of gas. So basically this is going to become 2. And at this position, once again, we get 3 units of gas. So 2 plus 3 minus, if we have to reach to next, which is from where we started, then basically it's going to be 5. So 2 plus 3 minus 5 is going to become 0. So basically we would be able to reach to unit number 4, and this is going to be the starting point if we were to complete the whole circuit. So we'll need to return the index position, so we can return 3 as the answer over here. And I know the explanation took a lot of time to understand what this problem statement is, but basically this is actually the whole solution as well. Because in order to solve this problem, we don't need to use any special data structure or any special architecture. Basically, if we just follow the most simple basic rule, that we are going to start our iteration from the very first index, and from this very first index position we are going to check that are we going in a scenario where our current tank goes negative. If the current tank goes negative, we can simply choose the starting point as the next element. And once again, if it goes negative, we can choose the starting point as next element, and we will keep on repeating the same process. And the moment the tank goes into negative, we will just update the tank value to become 0. And that is the whole logic of this problem to solve this problem. Now let's talk about some of the critical possibilities. Number one scenario is the only way we are not able to complete the whole circuit is a very simple logic. That is that if the given gas is going to be less than the total number of cost. If that is the case, cost is higher, so we would not be able to complete the full circuit. And we can calculate this immediately, basically by summing up all the values that are currently present in both gas and cost arrays, and we can just compare those values. So if that is the case, we can simply return -1 immediately, saying that this problem cannot be solved. If that is not the case, then we will simply follow the most common, most logical thing that humans are really good at, and that is called greedy approach. That we are simply going to take the first value, try the solution. If solution works, great. If we at any given moment find the tank goes into negative, then we will just pick the next value. So over here, for the same problem, I have just presented it in a different manner. Currently, we have our index position stored inside. So 0, 1, 2, 3 and 4. Now this second circle defines that how much amount of gas can we get at any particular location, and the values located at these gates define that if we have to jump from gate number 1 to gate number 2, then we will have to spend 3 units of gas, and which we can subtract. So basically the solution is that we will start our greedy approach by iterating at value number 1 with initially the tank is going to be 0, and then we will just repeat the same exercise we did. So we will check, okay, over here we can add 1 unit of tank, but this is going to be 3 units of tank to reach to value number 2. So tank would go into negative. So basically we would choose our starting point over here by resetting the tank to be 0. Once again 2, and this is 4. So tank goes into negative. So once again we would choose our starting value to be index position number 2. Once again tank goes into negative. So once again we would choose our starting index to be this. The moment we find a starting index where the tank does not go negative, we would try to iterate over and see if we are able to complete the whole journey or whole transaction. And basically we should be able to do it in this case, because we know that we have a starting point where the tank does not go negative from to when we start iterating. And secondly, the total cost of basically total cost is basically not greater than the total number of gas. So that's why we know that the answer should not be -1. And that's it. So in this case we would return 3 as the answer. If we have to calculate time and space complexity, it is quite straightforward. For time complexity, basically this can be done in big of n time if we apply the greedy approach and we do some slight tweaks with the code. So the tweaks with the code I'm going to explain you when we actually get to the coding portion. And for the space complexity, well, we are not using any additional space to solve this problem. So basically this is going to be big of 1, so which is quite beautiful. Now let's just quickly see the coding solution. So the solution is quite straightforward. First, we are going to have a few variables. They are going to be initialized as 0. First one is total gas and total cost. Both are initialized at 0. Then we have tank, and then we have starting index. Then we are going to have a simple for loop that is going to iterate over every single starting point in the given input. we are going to have two variables, total gas and total cost, that is going to be continuously adding the total amount of gas and total amount of cost we have. For the current proportion of gas that can live inside the tank is going to be calculated by adding the current gas with the current tank value, and reducing or removing the cost of the current ith position. Then we are checking for a simple condition that if the tank goes into negative, then the starting index that was originally at 0 now needs to be at I plus 1th position, because we identify that the current ith position does not work, and then the current value of the total amount of gas inside the tank is also going to be 0. Then we are going to check at if at any given moment the total amount of gas becomes less than the total amount of cost after the running of whole for loop. Then if that is the case, we can simply return -1, and if that is not the case, we simply return the starting index. And this is the whole solution. Let's try to run the code. Okay, seems like our solution is working beautifully. Let's submit this code. And our code beats 99.29% of all the other solutions, which is exceptionally fast, so pretty good. And once again, I would be posting this solution in our GitHub repository, so feel free to go ahead and check it out from there. Thank you. Hello friends, hope you are having a fantastic day today. So now we are going to solve an awesome LeetCode problem called hand of straights. Now we can see that this one is a medium problem and also a very well-liked problem on LeetCode. Let's understand the problem statement. We have a girl named Alice who has some number of cards, and she wants to rearrange these cards into a groups such that each group of the size group size consists of group size consecutive cards. So let's try to understand what this means. Basically, we are given an integer array called hand that defines bunch of different values inside a deck of cards, and at any given integer I is the value returned for that particular hand. Now we are also given another variable called group size. Now we need to check that whether we can divide all of these hands in a group sizes, like groups of these group sizes, such that all of the rearranged groups contains consecutive cards and we can rearrange all the groups. So let's try to understand this with an example, and then it would make much more sense. Let's say that we are currently given the hand or deck of hands like this, and we are given the group size to be 3. So let's see that can we create the different 3 size groups. So first group we can create is going to be cards 1 2 3. Now notice that there is a condition when we are trying to create the groups, that every single card inside the group has to be consecutive. So we can create this one group. Second group we can create is using these 3 characters, and that is 2 3 and 4. And third group we can create is using 6 7 and 8. So now notice that in this case we use all of the cards that were currently given to us, and we divided them into the size of 3, and each group contains the cards that were coming in consecutively. So in this case we can say that we can create the hand of straights using this, so we will return true in this case. Let's take one more example. Suppose the given hand is values 1 2 3 4 and 5, and in this case we are given the group size to be 4. So in this case we can create a group of size 4 with these 4 characters or with these 4 characters, both of which are going to have consecutive values. So values would be 1 2 3 and 4. The thing is, we would still have one more value left that is going to be left out, that we cannot use. So in this case we can return false, because we are not able to create or use every single card inside our hands array. Let's take just one more example. Let's say that currently the values given are 1 2 3 and 5 6 and 8, and in this case the group that we are trying to create is of size 3. So we can see that we can create a group 1 2 3 like this, no issues with this. We can also create a group of 3 cards using 5 6 and 8, but the thing is this is not going to be a correct group, because we need to create a group that only contains consecutive elements, and 5 6 and 8 are not consecutive cards. If this were to be 5 6 and 7, then it would have worked. So because of that, for this particular example we will have to return false. So that's it. This completes my explanation on what the problem statement is actually asking us to solve. Let's see that what is going to be the optimal approach to solve this problem. Well, the idea is quite straightforward. What I'm suggesting is that we are given currently the hands, and we are also given group sizes. Now we know that for this particular given group sizes, we will have to create groups. The values inside the group has to be consecutive. So first thing that comes to our mind is that if we are dealing with consecutive or subsequent values, why don't we just simply sort the given input of hands and then try to start creating groups according to that? Do you think that approach would work? Let's try to see that approach in action. Let's say that this is the current hand that we are given. Now we are trying to use our first approach where we are going to sort every single value inside our hand array and try to create groups of size 3. So the sorted hand is going to look something like this. Now notice in this problem, if we try to create groups of 3, we would not be able to make consecutive groups. We would run into this issue. If we create a group of 3, we would have a group that looks like 1, 2 and 2. And based on this, we can just say that this is a false group and we cannot make sense of it. But this would not be the correct assumption. Correct assumption would be that if we identify two values that are same in frequency, then we only need to consider the first value for the partition of first group. So the idea in this case would be that we would create a group that is going to be 1, 2, then we found a repeated character, so we would ignore this one and add value number 3 into a group. After creating this group, we will check that whether there has been any values that are currently left. So yes, this 2 has been left. So let's use the same operation. So now we are going to create one more group using this 2. Now notice that we have already used this 3 in the first group, so we are going to be eliminating that, and then we will have values 3 and 4 in this case. So we can also repeat the same operation, and then after all the values that we have currently used, we will keep on trying to make partition and trying to check that whether they follow the property of them being consecutive or not. So in this case, based on this approach, we can actually find the solution, which means number one, there are few assumptions we can make based on this. Number one, sorting is going to be greatly helpful. Second thing is, we come into the issue of duplicated numbers. So we will need to know that what is the frequency of every single character. And if we can combine these two values, store that information that have the sorted values of all the unique values that are present and have the frequency that how many times they are currently present, it would be easy for us to make these groups. And if we are able to make subsequent groups that follow all the property and we are able to use every single value inside the hand, we can return true or we can return false. So using this, what I'm suggesting is that we actually use something smartly. We use a hash map and we use a sorting approach. Now the thing is, why am I suggesting to use the hash map? Because we are dealing with unique entries, and for each of the unique entry we have different frequency, and this is what I'm suggesting that we store as part of the hash map, where as a key we are going to store that what is the current value of the hand, and as its subsequent value we are going to store that how many times that hand has been repeated in any particular iteration. Next, after storing this information, we will have to sort all of these given keys because we are trying to generate consecutive values one by one. So logically, why don't we just combine hash map and sorting at the same time, where we can simply use a tree map that is going to have best of both worlds, that can access and fetch all the elements in big O of one time, and it can insert all the elements in big O of log n time for the frequency and stuff like that, because based on the key value. So this is going to be an efficient approach. So now what I'm suggesting is that we are currently given our hand that we are going to be dealing with. For this particular hand, what we are going to do is we are going to create a tree map. This tree map is going to contain the unique value plus their frequencies, and for these two, using these two values, we will start creating groups of bunch of different numbers, and we will need to make sure that if the starting value of group is, let's say, 5, and the group has to be of size 3, then next value has to be 6 and next value has to be 7. If we can find 6 over here, that's great. If we cannot find 6 at any given moment, we can directly return false, saying that this group is not being able to make. So let's try to see my solution in action. So now based on the hand, we have our tree map ready. Notice in the tree map, we have every single key or the hand value is currently sorted, and we also have the frequency that how many times this is present. Now we need to create the group size 3 for every single value. So the idea would be that for very first group, we are going to take the smallest value out and we are going to reduce its frequency, and this is going to give us the starting point for that particular group. So starting point is going to be 1, which means this has to be a group of size 3. So next subsequent element that should be in the group has to be value number 2. But thing is, we are not sure if 2 is present or not. And lucky for us, we can check that immediately that whether 2 is present or not. By the way, when we took this 1 out, we would have reduced its frequency, so we can reduce the frequency to 0. The moment frequency becomes 0, it would make sense to completely eliminate that element rather than just storing it. So we can eliminate 3. Now we are looking for 2, we found 2, and which means we can also reduce the frequency of 2. So now the frequency is going to be 1. Next thing should be 3. So we are trying to find the 3, and we also found the 3 over here. We are also going to reduce its frequency from 2 to 1. So now this is also going to be 1, and we created our first group. Now for the second group, once again we will check inside our hash map or tree map that what is the smallest element, and this is going to be the very first value inside our tree map, that is starting point is value number 2. So now we are going to use value number 2 over here, which means its frequency is going to become 0. If the frequency becomes 0, we can mark it as 0, and then next element should be 3. So we will check that whether 3 is present. Yes, 3 is present. So we are also going to mark its frequency to 0. Once this becomes 0, we can also eliminate this value, and we can also now we are looking for next element to be 4. 4 is also present, and we can mark 4 as counted, so we can remove that element and close this group. Now after closing this group, we have basically deleted all the elements before that. Now once again we will have to create a new group, then that group starting point has to be 6. So we'll going to mark 6 over here, and then which means now we are looking for 7 and 8, and lucky for us 7 and 8 are also present, so we can just mark these as visited. And then in the end, notice that now we currently don't have any value inside our tree map, and because we did not find any place where we could not find an element, so in this case we can return true. Now let's say that in the same example, instead of this being 7, let's say that this value would have been 9. So in this case, what would have happened? That we would have values such as 6, and the frequency of the value is going to be that 6 is present one time, 8 is present one time, and 9 is going to be present one time. Over here we find that the starting point has to be 6. Now for this this group to exist, we will have to find value number 7, but 7 would not have been present over here. The moment we identify such thing like this, we could have written false immediately. So this is just for you to understand that under which scenario we would return false, and basically this is the whole solution. Now you can see how beautiful we are doing things. If we calculate time and space complexity, in this case the time complexity is going to be big of n log n. Why n log n? Because it takes us log n time to add all the entries inside our tree map. In terms of space complexity, because we are using an additional tree map, it is going to be big of n, but we can manage that. Now on top of it, we can also do one more optimization, that if let's say the given number of hands is currently 10, and if the given group is equal to 3, so if the total cards are 10, do we even need to check that can we make all the groups of size 3? No. Why? Because 3, we can only create like the group for 9 cards, and there is still going to be one more left out card. So initially we can always check that whatever the size of the given currently h is, if that is going to be divisible by the given group size or not, and this value the remainder has to be 0. If that is the case, then only we will move forward. So this would be a way for us to eliminate few like bad and edge cases. And now let's see the coding approach. Now for the coding solution, first thing we are going to check is to see that whether the given length of all the hands, so all the cards that we currently have, if that is divisible by group of 0. If that is not the case, then we can directly return false, because for sure we would not be able to make the group of that particular group sizes if this is not divisible by 0. If that is not the case, we are going to initialize a tree map where we are using hash map in combination with tree map, because we want to access the keys in a particular order. And now we are going to be counting every single card. So we are going to iterate over each of the card that is currently present inside our hand array, and we are going to be adding that to our tree map, where we are going to define that if that card is present as the key, then we simply update its frequency. If that is not the case, we create a new entry. Then we attempt to form groups, where we are first of all in the outer loop checking that while we still have present cards inside our key tree map, we are going to do the following, where first we are going to initialize the first key or the first starting point of the first group with the smallest key. And notice that because we are using tree map, we can actually just keep on accessing the keys directly because they would be stored in a sorted manner. Then we are going to iterate over the for loop, focusing on each particular group sizes, where we are checking that what is the current card, that is going to be first plus I. Then we are going to check if we have that current card inside our tree map or not. If we do not have that value inside the tree map, we can simply return false immediately because we cannot make consecutive groups. If that is not the case, we are simply going to add that value. Then we are going to reduce the value or the decrease the count because we are removing the card. And then we are checking that if the given count is equal to 1, then we can simply remove that card completely from our tree map. If that is not the case, we simply reduce its frequency and repeat the same operation. If we do get out of this loop, which means we are able to get out of every single card and use every single card to create the appropriate group sizes, and which means we need to return true in the end. So this is the whole solution. Let's try to run our approach. Seems like our solution works beautifully. Let's submit this code. And our code beats good chunk of solutions. It is not the best and there are still improvements can be made, but given the time frame, this is a good approach, and the solution is present inside our GitHub repository. So feel free to go ahead and check it out from there. Thank you. So as you can see, this is a very well like LeetCode problem, and also this is a LeetCode medium problem. Now let's try to understand that what the problem statement is asking us to solve. Basically, we are given a non-negative integers nums array, and we are being told that we need to arrange this in such a manner that we get the largest number from combining all the numbers that are currently present inside the given array. So let's try to understand this with a couple of examples. If we see this first example, we are given an array with two values, 1, 0 and 2. So if we combine these two numbers, what is the largest number possible number that we can get? So in this case, we cannot break apart this existing number. So 1, 0 has to remain 1, 0 in all the cases, but we have the option to select from 2, 1, 0 or 1, 0, 2. So because currently we only have two values, so we only have two possibilities, and in this case 2, 1, 0 is the largest number, so we need to return 2, 1, 0 as the answer. Let's try to understand the same problem with few more examples. So suppose we are given the values like 3, 5 and 10. If this is the value given to us, what is the largest number we can make out of this? So one option is we can make a value 3510. Second option is we make a value like 5310. Next we can make a value of 5103, something like this. But in either cases, amongst all the possible values, this is going to be the largest value we should be able to make. So in this case, we need to return this as the answer. So I hope my explanation makes sense to you and you can understand that what we are trying to return. Now, if we see the problem statement, we are given a couple of other things to make our lives easy. Number one, they are saying that the result could be very large numbers. So we need to, rather than returning integer values, we can simply return string as the answer. And all we are doing in this problem is that we are actually treating these values as string values, so string 1 and string 2, and then we are seeing that how can we concate string 1 plus string 2 in such a manner that we get the largest number. So we have two options because we currently only have two values, string 1 and string 2 in this case. So either we can concate string 1 plus string 2, which would result in the value 102. which is this value combining these two numbers, or second option is we concate string 2 plus string 1, and in this case the answer we get is 210. So because 210 is larger than 102, we are going to return 210 as the answer. Now this is a very clear hint on how we are going to solve this problem. Basically the idea is that we could have been given bunch of different values inside the given array, and somehow we need to sort this array in such a manner where the very first element is the largest value, and we are not talking about largest in terms of like pure numerical value, but the largest first value, and this we can only determine compared to rest of the other values. And I know what I just said might have gone over your head, so let me give you try to give you a simple explanation. Okay, let's just go back to our example of values 3, 5 and 10. Now in this case we know that the answer is going to be 5310, and this has to be the largest number. But how can we come up with this largest number? And if we have to make this number, what should the sorted array should look like? So the sorted array should be that very first value should be value number 5, next value should be value number 3, and the last value has to be value number 10. Now if we just take the example that in this given input array we are simply trying to make the largest value as the numerical sorting order and then present that largest value as the sorted array, then it would not work. Because if you see in this case, if we just have to sort all of these values based on their value preposition, we would get a value like this 10, 5 and 3. But in this case, if we combine these letters in this sequence, we would get value 1053. So 1053 is clearly a smaller value compared to value 5310, which is what we need to return. So what I'm suggesting is that whenever we start sorting the array, the logic we are going to use is that let's assume that we want to compare two numbers. So currently the two numbers we are comparing is 5 and 10. Okay, these two numbers. So what are the options we can have? Number one option for this array is that either 5 can come before value number 10 or 10 can come before value number 5. But in either case, how we are going to determine? We are going to determine by combining these two values as if they are string concatenation, and let's see that what approach we come up with. Okay, so now currently the premise is we only have two values 5, 10 and another value is 10, 5. So which sequence should be the correct sequence? So we are going to combine the values. So if we combine this, we get the value 510. If we combine this, we get the value 105. And in this case, 510 is clearly greater. So when we are sorting our array to generate the largest number, 5 has to come before value number 10 somewhere. And this is the logic we are going to apply to solve this problem. So I'm going to show you two examples of solving this with like a simple problem and a complex problem, and that would enable your mind to come up with the answer. And if you are having any issues or if you are not able to comprehend what I'm suggesting, all I say is that you apply this logic to sort the array and you should be able to find the answer. So this next portion is for anyone who got confused. So that then just look at the example. But if you already understood what I'm trying to say, then you can basically conclude this video. So now let me just explain my theory with a couple of examples. So number one example is once again, let me take three values. Okay, so 7, 2 and 9. Okay, these are the three numbers we are taking, and we know the biggest number we would be able to make is going to be 972. Okay, let me take a little bit more complicated value because this is very simple. So instead of 2, we are going to take the value 20. Okay, and now the largest value we should be able to make is 9720. But let's see the approach. So first what we are going to do is we are going to apply the same logic that when we are comparing two values A and B, we are going to compare A plus B and we are going to compare B plus A. And this is not plus as in like mathematical plus, but you can consider this plus as a concatenation of two numbers. Okay, so now currently the two values we have is 7 and 20 we are trying to compare. So what are the two options? Number one option is that we have 720. Second option is 207 because this 20 has to remain together. So amongst these two values we can clearly see that 7 is greater value and 20 is lesser value. So after comparing these two elements, we can conclude include that 7 has to remain first and 20 has to remain second. But now we still have to make sure that where we are going to put this value number 9. So once again, let's compare this value number 9 with this value number 20. So if we compare 9 and 20, we have one option is 920 and second option is 209. So clearly 920 is greater, which means 9 has to come before value number 20. So let me make this adjustment, and currently 9 has to come before value number 20. But is 9 at the correct place? No, because we still have to check with value number 7. So once again, we are going to compare the value 79 and 97. Once again, 97 is greater, which means 9 has to come before value number 7. So let us also adjust the value of this 9. So now currently this 9 is very first element and this 7 is the second element. Now since we ran out of elements over here, which means we can't do anything in this case. So this has to be the correct sequence of numbers that are sorted in ascending order such a way that combining these is going to result the largest number possible. So let's combine these values and the answer is going to be 9720, and this is what we need to return. Let me give you just one more example really quickly, just for the explanation sake. And let's take some larger examples. So the values are 3, 50, 20 and 9 and 1. Okay, this is the number. So let's start comparing. So first we compare this value 3 and 50. So one option is 350 and second option is 503, which means definitely 50 has to come before value number 3. So okay, now currently we are comparing this value number 3 with value number 20. So once again, if you do that, 203 versus 302, oh sorry, 320. So once again, 320 is going to be greater. So we are going to put 3 before value number 20. This is correct sequence. Now 20 compared to 9. So once again, the one option is 209, second option is 902. So definitely 9 has to come before 20. And once again, if we keep on repeating the same process with 3, once again 9 has to come before 3 as well, and same way 9 has to come before 50. So the value is going to be 9, then 50, then 3, and then 20. Okay, and last value is 1. So 1, okay, if we compare 20 with 1, the answer is going to be 201 and 120. So 201 is greater, so value has to be 1. And if we combine all of these values, this is the correct sorted order, and I really quickly glance over it because I just wanted to explain how the method is going to work. And the answer is going to be 9503201, and this is going to be the largest number we should be able to make from given this input, and this logic would work perfectly fine. Now for most of the languages like Java, Python, C++, they already have a sorting method in order to sort the arrays, and we can sort them in any order. So even for this one, we should be able to take or utilize the sorting method in order to generate the array. And this sorting usually works in n log n method, where we use comparator method to compare any two elements in order to sort them. What I showed you over here was a very slow approach. This would work in big O of n square time, but since we already have a sorting method that is built in that runs in n log n time, we should be able to use that, and that is going to yield us very good result in terms of time complexity. If we see space complexity is going to be big O of n, because many cases this sorting algorithm usually takes big O of n space, and that's these are the time and space complexity. Now let's try to see the coding solution. So very first thing we are going to do is create a new string array, because we will have to convert all the numbers into the string, and then we are going to iterate over our given nums array into simple for loop fashion and convert all the values into the string values. Once we have our string array, now all we need to do is use the pre-existing arrays.sort method, where we are comparing two elements in such a manner that we are concatenating the strings a and b, and we are comparing a plus b and b plus a and seeing that which value is greater compared to the other value. Once this is done, the array should have been sorted. Now we are just taking care of one of the edge cases, where if the given value has the largest value or the very first element as 0, we can simply return 0. If that is not the case, we will simply run a string builder operation, where we are going to concate all the values that are currently present inside our string array, which we have already sorted in ascending order in terms of completely larger values, and then we can simply return the largest number that we have been able to build using our string builder method. So now let's try to run this code, and seems like our solution is working as expected. Let's submit this code. and our code runs very fast compared to a lot of other solutions, and it is also very efficient in terms of memory usage. So I would be posting this solution into the GitHub repository that we have created. And if we see, this GitHub repository contains hundreds of different LeetCode code solution questions and answers, and I will be posting there, and the link to this GitHub repository is currently present inside the description of this video. So I hope you like it, you enjoy it, and till then, take care. Hello friends, we are still not employed by a FANG company, so let's not stop lead coding till we get there. Today we are going to do maximum sub-array lead code problem, and if we see some of the companies where I want to get a job who have already asked this question, there are companies like LinkedIn, Amazon, Apple, Microsoft, Google, Adobe, Facebook, Bloomberg, Uber, ByteDance, Yahoo, eBay, and Splunk. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode medium problem and very well liked problem on LeetCode. Basically, we are given an array called nums, and we need to find a continuous sub array which has the largest sum and then return the sum value. We are also told that a sub array is a continuous part of any array, so we are given the definition of it. Now let's try to understand this with an example. So suppose this is the example we are given. Well, I have actually drawn this example in much bigger format over here. So for this example, what we are going to do is we are going to see different sub arrays, and then we are going to see that what is the maximum sum we are able to find so far, and then in the end we will return whatever the maximum sum we have found. So first of all, this value is actually -2. So because this value is -2, even if all the remaining values they are positive, it makes no sense for us to keep this value. So we are going to ignore this value and we are not going to keep it in our current sub array. Now this value is +1, so that is good. But again, combination of these two is actually -2. So again, we cannot keep this in the our continuous sub array. Well, now this value is actually +4, and which is good sign. Now these two values, this is again still +3, which is also a good sign, and the combination of these three is again 5, and then we add this value, so this becomes 6, and we are going to keep on updating the max value as well. So max value so far we have found so far is 6. That we can say that up until this point, the sub array there where we have found the maximum value to be is 6. Now this is again -5. So if we do 6 plus -5, we still get +1 value, which is again positive. So we are keeping this as a sub array, and then again this value is +4. So +4 plus 1 becomes +5. So this is also positive. The thing is, in the end, up until this point, the maximum value we were able to find is 6. So because it was 6, we are going to return 6 as the answer. This is what the problem is asking us to do. We need to find the sum of maximum sub array and then return that value. So let's see what would be different approaches to solve this problem. Basically, we need to find the maximum sub array. What we can do is we will try to find every single possible sub array, try to see the sum of all of those characters, and whichever possess the maximum sum, we simply return that sum. So let's see that in action. So first of all, what we are going to do is we are going to take some of this character, then we are going to take some of these two characters, then we are going to take some of these three characters, and so on and so forth. We are keep on repeating the process with the first element. After we are done with this, essentially we are going to get rid of this first element, and now whatever the remaining elements are, we are going to start taking some of those values. So in this case, what again we are going to do is we will take this element, then again we will take these two elements, and again we will take these three elements, and overall we will keep on making the sum, and eventually we would find the answer, and the answer in this case is going to be the sum of these three characters, and whatever the answer is, we can simply return that. So this approach would work as expected, but the issue with this brute force solution is actually that we are doing a lot of repetitive work. If we see the time complexity in this case, the time complexity is actually going to be big O of n square. So let's see that what would be the better way to solve this. Before we come up with the optimal solution, first of all, let's make a couple of things very clear. What is our aim and what is the thing that we are trying to find? Well, basically we are trying to find that what is the maximum sum sub array. At any given moment, there can be any current subarray that we are iterating over, which could be the maximum subarray or could not be the maximum subarray. We don't know. But at any given moment, we will need to have the ability to keep track of sum of all the characters that are present in that particular subarray. So which means that we are going to have a variable called current or current subarray, where we are going to keep track of the sum of all the current variables that we have iterated over and we are keeping track of. Well, second thing is, that we need to find the maximum subarray, and amongst any of the subarrays, anyone could be the maximum subarray. So we are also going to keep track of another variable called maximum subarray, where we are going to keep track of maximum current sum we have found so far. So well, these two things are understandable, right? They are from programming perspective. But there is also one more thing that is actually rational, and the rational thing is that at any given moment, suppose this value is actually -3. So current sum or current sub array we have found is actually -3. So if this value is -3, because this value is negative, so if this value is negative, even though all the remaining values they are positive and they keep on increasing the value in size, this -3 is always going to have to cause them to have a lesser value. So if that is the case, why are we even bothering to keeping this value at our bay or at our disposal? So the idea is at any given moment for our current subarray, the moment we would identify that the current value or some set of current values, they are causing it to have a negative value. If that is the case, we are going to immediately update our current subarray, and then we will keep on moving towards the next values. And based on these two logics, all we are going to do is we are going to iterate over our given array and keep on going to updating the current subarray, and then keep on updating the maximum subarray we have found so far, and in the end we should be able to find the answer. So let's see that traversal in action. Before we start iterating over this array, we are going to define some default values for this current and maximum variable. The default value for current is going to be the 0, and for maximum it's going to be whatever the first element of this given array is, which is -3. That is to cover an edge case where we are only given one element. Now let's start iterating over. Okay, so now the sum of these two elements is actually going to be -3 plus 2. So -3 plus 2 is actually going to be -1, which is still less than 0. So because this is less than 0, we are not going to update our current max variable, and the maximum sum we are actually able to find so far is going to be 0, which is definitely greater than -3. Now again, for these three variables, again the sum is going to be negative, so we are not going to do anything, and we are going to ignore all three of these cases. Now this value is actually positive, so because this value is positive, the current sum we have is going to be 8, so which means we will have to update the maximum sum we have found so far to be the value 8 as well. Now again we add the sum of these two values, so 8 plus -1, so 8 plus -1 actually becomes 7. So this becomes 7, which is less than whatever the maximum value we have found so far, so we don't need to update the max variable. Now we again add this value to our current sum, so 7 plus 2, 7 plus 2 is 9, 9 is greater than whatever the maximum value we had, so this becomes 9. Okay, now again this is also a positive value 3, so we can do 9 plus 3, which becomes 12. So we are again going to add the value 12 to our maximum sum that we have been able to find so far, and then this value is actually -5, so we can do 12 plus -5, so 12 plus -5 is going to be 7. And again, because this value is still positive, we are keeping this current subarray going on, because we don't know, future values might be positive values, and this can also go up pretty quickly. Now we have actually reached to the end of this array, and we don't have any more elements to go over, so the maximum sum we have found so far is 12, and this is what we need to return as the answer in this case. And so this is the most optimal approach to solve this problem. If we see time and space complexity, in this case the time complexity is actually going to be big O of n. Why big O of n? Because we will have to iterate over every single array, or every single value that is present inside this given array, which takes big O of n time. If we see space complexity, in this case the space complexity is actually big O of 1, or constant space, because apart from storing these couple of variables, we are not using any additional space, so that's why space complexity is very minimal. First of all, we are going to initialize two variables called current sum and maximum sum. For current sum, we are going to initialize the value to be 0, and for maximum sum, we are going to initialize the value to be the first value inside this given nums array. We are going to create a for loop to iterate over this given array. Now we are going to check that whether the current sum, if that is less than 0 or not. If that is less than 0, we are going to update the value of current sum to 0. That is not the case. We are going to calculate the value for current sum and maximum sum. So current sum is going to be current sum plus whatever the current value inside this given nums array we have. And we will have to check that whether the current sum we have created, if that is the maximum sum or not. And after loop ends, we simply have to return maximum sum. Let's try to run this code. Seems like our solution is working as expected. Let's submit this code. and our code runs pretty efficiently. I would be posting this in the comments so you can check it out from there. Thank you. The lead code problem we are going to solve now is called merge triplets to form target triplet. Now we can see that this one is a medium problem and also not very well like problem, but a really important one. Basically, a triplet is an integer array of three integers. Okay, that's fine. And we are given a 2D integer array called triplets with bunch of different values that contains the pieces of triplets, which means like values like A, B, and C. Okay. Now we are being told that there is a target triplet X, Y, and Z. Now we need to make sure that in this given triplets, are we able to generate this target by doing the following operation on any number. So basically we can pick any two triplets from our given triplet array, and if we pick any two triplet, basically we can combine them to create a separate new triplet that is only going to contain three values, but that is going to be the maximum value at each position amongst these two triplets. So let me give you an example. Suppose we have a triplet 1, 2, and 3, and we have a triplet, let's say 4, 5, and 6. So in this case, we know that amongst these two, the higher value is 4. Then amongst these two, the higher value is 5, and amongst these two, the higher value is 6. So if we merge these two triplets, basically we can form an operation like this. So based on this, we are being told that we can do as many number of operations as we need amongst all the triplets that are given, but we are trying to make this target number. If we can make the target number awesome, we need to return true. If we are not able to make the target number, then we need to return false. So let's try to see one example, and we'll try to figure out different examples from that. So first one is that let's say that in any given case we are given these three triplets, right? For these three triplets we need to form a number 2, 7, and 5. Now notice that we have the option to do the operation between any two triplets. So let's say that we do that max operation between these two triplets, which means we have value 2, 5, and 3 at one position, and second value is 1, 7, and 5. By doing the operation like the merge operation, basically we can pick the maximum amongst the all of these values, and we will form a new triplet that is going to be maximum of these two values. So the value is going to be 2, this is going to be maximum, so value is going to be 7, and this is going to be the maximum, so once again value is going to be 5. And notice that this exactly matches the given input target that we have. So in this case we can return true, saying that yes, based on the given input we are able to generate the target value, and hence we can make the triplet by merging two triplets. So let's see that what is going to be the brute force approach to solve this problem. Well, it is quite straightforward that for any given triplets that we currently have, let's say that we are given in total 5 triplets, and I'm just marking them as A, B, C, D, and E. And for each of these 5 triplets we have the option to do the merge operation. So if the brute force ways that we do merge operation amongst these two triplets, we do merge operation amongst these two triplets, and so on and so forth, we keep on repeating, and every single time we compare it with the target value to see if we are able to generate the target value or not. And eventually if we can, we would find the correct answer, but this would yield in big O of n square time, where n is the number of triplets that we currently have, which is an inefficient approach. We'll need to find a better approach, and the optimal solution in this case comes from doing things in the most simplest manner optimally, and that is to use a greedy approach. So let's say that this is the example that we are currently given. Now notice that whenever we are iterating over any particular triplet, we should always compare it with the target to determine that is this a triplet of interest or not. And the comparison should only contain two items. First thing is that whether if each of these three values, if all of these are lesser than the target value, then and then only it is a triplet of interest for us. Otherwise we need to move on to the next triplet. And why? Let's try to understand. Let's say that currently we are given a triplet 2, 6, and 5. and we are given the target to be 466. Okay, so in this case we can notice that every single value, so 2, 6 and 5, comparing with 4, 6 and 6, notice that every single value inside this triplet is actually less than or equal to the target triplet that we have, which means this can be a potential candidate that we can use in future for the merge operation. Now the thing is, if we are going to use this for the merge operation, then we should just put this on a side, and noting that we found a triplet which can be of potential use to us. At the same time, we should also have to keep track of a variable that what if we already found a triplet that we are all anyways going to find the optimal solution with. And in order to do that, we will have to basically compare the given triplet with the target triplet and keep track of the maximum value that we are able to generate from both of these triplets and just store that information. So let's say in this case, we can notice that because this is a triplet of interest, then we are going to store the maximum value amongst these two and these two. And notice we are having a condition that this has to be smaller or equal to the target, which means either we can have all the values that are going to be smaller than target, or it is equal to target, which means we would never exceed target in this approach. So in the maximum variable, we are going to compare the max values. So we are going to, this is going to be 4, this is going to be 6, and once again this is going to be 6. Okay, so we took care of this triplet. Now let's move on to the next triplet. Once again, in the next triplet we have a value called 7, 4 and 6. Now notice that for this one, for 7, 4 and 6, we did found a triplet that we currently have over here that is of potential interest, could to target or not. So notice that the very first value 7 and 4, so 7 is greater than 4, which means if we do merge operation with this triplet, then we are always going to have first value that is going to be greater than the target value, which means this would not be a use for us. So we should just simply skip over this triplet, because we should not use this triplet to merge with anyone else. Okay, next we have this value 4, 4 and 6. So let's try to see that if we use this value, what is going to be the expected range or expected triplets we are going to be find. So in this case, basically once again, we compare 4 with 4, so this is equal, 4 with 6, so this is lesser, and 6 with 6, so this is equal. So once again, this can be a potential triplet that we can use. So now let's try to do the max operation in this case. So the current values are 4, 4 and 6. So we are doing 4, 4 and 6, and we are comparing it with the target, which is 4, 6 and 4. So now notice that maximum amongst these two is going to be 4. So we add 4 over here. Maximum amongst these two once again is going to be 6, and maximum amongst these two is going to be 6. And now in the end, we are going to have a maximum variable that is going to contain values 4, 6 and 6 over here. And meanwhile, we are going to have another target value that we were trying to achieve, and that was also 4, 6 and 6. So notice that because both of these values match, we can simply say that yes, there exists a triplet that we can generate by merging other triplets. And if we cannot find this maximum value, which means there does not exist a triplet that is of a good use to us, so in that case we would have returned false. So if you see approach for this solution, then we can simply run it in big O of n, where n defines the number of triplets, and in terms of space complexity, we are not adding any additional space, so this is going to be big O of 1 as well. So I hope this solution makes sense. Now let's quickly see the coding approach. The coding solution is quite straightforward. First, we are going to initialize an array with size 3, naming it as max values. Then we are going to iterate over every single triplet that we are given inside our triplets 2D array. And for each of the pair, we are going to check that if the current triplet that we have, will it be contributing towards making the target or not. So we are checking that if the given triplet position, the first value is less than the target, less than or equal to target, second value is less than or equal to target, and third value is less than or equal to target. If that is the case, then we are going to simply update the maximum values we have been able to achieve based on the given current triplet and the target values. Now remember, because we are considering triplet values to be less than or equal, which means if The only case where we have the target value set as it is if the given triplet value is also same as target value, that subsequent value. So we are going to store the values for all three parameters and keep on repeating the same process for every single given triplets in a greedy fashion. In the end, we simply have to check that whether the three values present inside our array match the target values that are present. If that is the case, we can return true, otherwise we can return false. So let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs beautifully, and it is pretty fast. So I will be posting the solution in the comments so you can check it out from there. Thank you. Hello friends, we are still not employed by a FANG company, so let's not stop lead coding till we get there. Today we are going to do jump game problem. Recently this problem has been asked in Amazon, Facebook, Apple, Google, Oracle, TikTok, all these gigantic companies, and they are some of my dream companies. So I'm going to do my utmost focus for this video, and I hope that you find it enjoyable. This is going to be the framework for the video. First we are going to understand the problem, then we will come up with a brute force approach. We'll improve our brute force approach, we'll find the optimal solution, and then we'll write the Java code for the optimal solution. This is a medium problem, and we are given an integer array nums, and we are initially positioned at the first index, so 0th index. Each element in the array represents that that is the maximum jump we can take, and if that is true, can we reach to the last position. So if we are able to reach to the last position, we would return true. If we cannot reach, we will return false. So let's understand this with an example. Suppose our given input is like 2, 3, 1, 1 and 4, and initially we are located at this position. This is the same example over here. So we can see that if we over here, we can take maximum 2 jumps. So either we can take 1 jump and reach over here, or we can take 2 jumps and reach over here. Let's get the greedy approach, and we'll take the maximum amount of jumps. So over here, if we take 2 jumps, we end up over here. Over here the maximum jump we can take is only 1, so we'll reach over here. Again the maximum jump we can take is just 1, so we'll reach over here, and this is our last position. So since we have reached over here, which means that we can conclude that we can solve this jump game, and we can reach to this end position. So we'll return true in this case. Now let's take one more example. So suppose we are given input like this: 3, 2, 1, 0 and 4, and if we check for the possibility, so over here the maximum number of jumps we can take is 3 jumps. So if we take 3 jumps, we reach at 0. From 0 we can't move anywhere forward. So let's, rather than taking 3 jumps, we'll try to take 2 jumps. So if we take 2 jumps, we end up over here, and over here the maximum we can take is just 1 jump. So again we end up at 0. And lastly, rather than taking 2 jumps from here, we'll just take 1 jump. So we'll end up over here at this position number 2. Now at this 2, the maximum jumps we can take is 2. So again we end up at the 0, which means that in any circumstances, if we start at this position number 1, we cannot reach to this last position. So over here we would return false. This is basically the problem statement. I have given a custom example that we are at any position, we are going to first of all see that what is the maximum jump we can take. We'll try to make that jump. We'll try to see that using that jump, if we can reach to this end index. If we cannot reach to the end index somehow, we will backtrack. We will go back to the position where we initially took the jump from, and we'll try some other possibilities. So let's see that in action. So over here we are initially at this position number 2. The maximum jump we can take is at value number 2. So that jump will bring us over here. Now over here the maximum jump we can take is at this position 0, which means that we can't move any further. So we will backtrack. We will come back over here. Now again we are at this second position. Now let's, rather than taking the 2 jump, we will reduce our jumping possibility and we will just take jump of 1 step. So now we reach at this value number 3, and over here with this value number 3 we can take maximum jump of 3 steps, which means that we can, if we take 3 steps, we will end up over here. So 1 2 3, and at this position 2 the maximum number of steps we can take is 2, which means that even if we take 2 steps we will cross our last entry, which means that in any case we would be able to reach to this last element and we would return true in this scenario. Now this approach seems sensible on pen and paper because we are dealing with a small number of things, small number of input, and we are able to clearly see that how the pattern is going on. So let's take another example. So these are the values. Let me also denote the index values for these. Now with every single iteration, I'm going to note down the index value transition we are making. Okay, so initially we are at this position number 5. The maximum jump we can take is a 5 step, which means that we would end up over here. So initially we would do something like this. So 0 to 5. This is one step we take. We are at 0 position, which means we can't go forward, which means we have to backtrack, which means that again from 5 we will come back to this 0th index. Now from 5, rather than making a jump of 5 steps, we will make jump of 4 steps and we would end up at this position 4. So from 0 we would end up at this position 4. Now from this 4 the maximum jump we can make is 1. So again we will take 1 step jump and we would end up at this position 5. Again from we are at 0, we can't do anything, so we will have to backtrack. So in order to backtrack, we will go back to this position number 4. Again we have to backtrack from this position 4, so we will end up at 0. Again we will, rather than making a jump of 4 step, we'll make a jump of 3 step and we'll end up over here. So we end up over here, and so on and so forth. So you can see that this in this approach all we are doing is just we are going someplace, we are coming back. Again we are going, and then again we are coming back. Again we are going to some next element, we are going to some next element, and we are coming back. And suppose this keeps repeating multiple times, you are essentially depleting your resources, because if you see the time complexity at any single iteration or at any single value, we have two possibilities: whether we want to keep this value in our current transition, or we do not want to keep our value, keep this value in our current path that we are calculating. Which means that the input, if we make decision tree, the decision tree would keep on growing and growing with addition of every single value, which means that we are basically making a lot of decisions, and the time complexity in this scenario would actually be big O of 2 to the power n, because at every single position we are making two possibilities. This is a very bad exponential time complexity which we cannot allow in any scenario. Okay, so the issue in the brute force approach we had is that we were doing a lot of repetitive work, because at any point we found out that we are not able to make any progress from this point. We are still ending up at that point. So let's see that how can we counter that with a better approach. Suppose we create an additional data structure over here. So we create a dynamic programmatically additional data structure over here. Let's create an array, and in that array we are going to define that at any position can we reach to this endpoint, and if we identify that yes we can reach to this endpoint, we would basically fill that position as true. And let's see that how it can help us. So if at any point in time we are at this final position, we know that this is the main terminating case, which means that we can put true over here. So this final element we can always put true, and this would actually become our base case. Now we have a base case. We are going to start iterating on from right to left manner, and we are going to start filling up our DP array to see. And in the DP array, the only thing we are mentioning is that at any given location, if we are able to reach to this endpoint or not. If we can, we'll just mark it as true, otherwise we'll mark it as false. Okay, so now one step over here, this is this value has potential to make two jumps, and it only takes one jump to get to this last point, which means that if we end up at this fourth position, we can reach to this fifth position, which is what we want. So over here we can also fill this as true. Now we are at this zeroth position. From the zeroth position, can we reach to this fifth position? No, because we can basically can't make any jumps. So we'll just fill this as false. Okay. Now from this one, can we end up at this fifth position? So we are going to, now the interesting part comes. Now we are going to check that, okay, this has possibility of only doing one jump, right? So with one jump, we can only end up at this third index. Now we only need to check that in this DP array for this third index, if the value is true or false. So in this case, this is already false, which means that the maximum we can get to is this third place. From this third place, we can't go anywhere. So we don't even need to check these values. We can only check this DP table, and we can conclude that no, we can't go anywhere forward. So we will put a false over here as well. Now we are at this third position. Now from this third position, we will again do the same check, but the thing is this has potential to do three jumps. Okay, so let's do one jump at a time. So first we take a jump. If we take a jump of one step, we end up over here. We check over here that this is false, which means that this is false, right? Now we take second jump. With the second jump, we end up at this third position. We check in this DP array. This is also false, which means that we can't do anything. Now from this third position, we still have one more possibility, that we can take a jump of three values. So if we take a jump of three values, we end up at this position, value number, this index number 4. So for this index number 4, we see that the value is true. If we find any true, which means that we can say that from this second, this index number 1, we can reach to this last endpoint. And now for this position, we need to check that it has potential to do two jumps. We will only check for one jump. So with one jump, we will end up at this first index. That one is true, which means that we can fill true over here as well. And in the end, we just need to return whatever of DP of 0 we found. So in this case, we can determine that this is true, which means that we are able to come to final endpoint. So this solution is very good. It works perfectly fine. Okay, so the time and space complexity for this approach would be, so the time complexity would be big O of n square, because notice that we need to do one iteration to go on for every single element, and sometimes for any given element we might have to do multiple jumps, like we did in this case of 3. So in the worst case, we might have to solve this in big O of n square time, and the space complexity would also be big O of n, because we are creating this additional DP array. Now this is still much better than our brute force approach, but our aim is to go into companies like Google, Facebook, Amazon, Apple, and whatnot. So those companies expect the best out of the best solutions. And is this the best out of the best solutions we can do? Actually, no, there is still a better optimal solution, and let me show you how we can get there. Okay, and this optimal solution is actually based on the dynamic programming solution that we just saw. So in dynamic programming, what we are doing is we are creating an additional DP array, and we are storing that whether we can reach to this last element or not. But the thing is, what if rather than storing this value at any position, when we find out that, suppose from this position we found out that yes, we are able to reach to this last position. So why do we need to check that whether we can reach to this last position or not? If at any point amongst these values, if we end up at this position, we would still be able to guarantee that we can reach the last element, because we have already checked this condition. So rather than checking for this whole thing, if we just check that, okay, from here, if we can reach to this element or not, and if this is true, we can simply return true at that moment also. And let's see that in action. So let me clean this up a bit. Let's mark all the index values. Okay, initially we create an element called final, and this final element represents the last value in the given input, and initially we set it up to this index number 5, right? Now our aim is that at any point we found out that amongst these values, if anyone can reach this final element, then that element by itself becomes this final. So rather than storing all the values of at any given location, we are actually shrinking down our boundary of search. Initially the final is at this 5th position, now we are at this 2nd position. So all we need to do is to check that whether our current index our current index and this current value, if sum of these two is actually greater than whatever final we have. So currently the final we have is this 5. So this is the final we have. Current sum of these two values becomes 4 plus 2 is equal to 6, which is greater than 5, which means that we can update the value of our final. So now this becomes our new final, and we basically don't care about this value anymore. Now we are at this 3rd location, and we try to see that the index plus its value. So this becomes 3 plus 0. Is it greater than our final? No, this is not greater than our final, because this is 3 and this is 4, which means that we can't do anything over here. So we drop this calculation and we check with the next element. So over here we have this 2 and we have the value 1. So 2 plus 1, is this greater than 4? So greater than final? No, this is also not true, which means we can't do anything over here. We again go back. Now this is 1 and this is 3. Now 1 plus 3, is this greater than or equal to value 4? Yes, this is greater. This is actually equal to 4, which means that we, from this point, we can come to this point. This is what this concludes, and which is what we want, right? So now we know this information, which means that we can update the value of our final again. So now the value of our final would become 1. So at this value, and now at this 0th position, we need to check that whether we can reach to this 1 or not. So over here the sum of these two value becomes 0 plus this is 2. So 2 is definitely greater than the final amount we have is 1, which means that we can reach over here. So the final element would be shifted to this point, and at the end of our iteration the final would be 0. So now the final is 0. After the end of the iteration, we only need to check that what is the value of final. If final is 0, we return true. If final is anything other than 0, we return false. And this is a very good solution. The whole thing runs in the time complexity of big O of n. And if we see the space complexity, we are only storing one additional parameter. So we are essentially using constant space, and we are solving this problem. So this is a very efficient solution. Let's create a variable called final. Oh, it's Java, I can't use final. Let's call it final with an extra L, and we'll assign its value as nums.length -1. And now we will run a for loop, and we'll start it from I is equal to number of length nums.length -2, because we already know the result for the array length, and we will run it up until we reach to this 0th position. We'll do I minus minus, and inside the loop we are only going to check one condition, that if the current value of I plus nums of I, if they are greater than or equal to whatever the final value we have, we can update the value of this final parameter to whatever the ith value we have. And yeah, that should be pretty much it. Now we only need to check that if the value of this final character is 0 or not. So if it is equal to 0, we can return true, else we can will return false. Okay, let's try to run the code. Seems like our solution is working. Let's try to submit the code. Okay, our solution works 100% faster than all the other solutions. This is really good sign, and this is not constant time, but because we are basically shifting our boundary, we are essentially reducing the number of work we can do. And also, if you see the memory usage, we are actually better than 86% of all the other solutions. So this was a very small line of code, but this small line of code actually requires huge set of understanding. So see you in the next video. Thank you. If we see some of the popular companies who have already asked this question, there are companies like Amazon, Google, Goldman Sachs, Bloomberg, DoorDash, Uber, Microsoft, Apple, Tesla, TikTok, Snapchat, and ByteDance. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode medium problem and also very well like problem on LeetCode. Basically in this problem we are given an array of integer called nums as an input, and we are told that we are initially positioned at the first position inside this given array. Now our aim in this problem is to return the minimum number of jumps required to reach to the last position. Now you must ask that how are we going to make these jumps? What are the criteria for that? So the criteria for any jump is that any given value that is presented inside this given array represents the number of values it can jump. So basically if this one is represented 2, we can say that it can reach, it can either take like one jump or it can take 2 jumps and reach to these positions. And our aim is to reach this last position, and basically we need to do this in the minimum number of jumps that is required. Now if you are confused, don't be. I'm actually going to show you a couple of examples to understand that how things work. So basically over here we are given 5 different values, and for these 5 different values, as I mentioned earlier, every single value represents the maximum number of jumps it can take. So this value number 2 has 2 possibilities. It can either take 1 jump and reach to this position number 3, or it can take 2 jumps and reach to this position number 1. Same goes with value number 3. It has 3 options. It can take like 1 jump, 2 jump, or 3 jumps, and then do that. And our aim is to reach the last position from the first position in the minimum number of jumps possible. So if we see in this example, the answer is actually quite evident. We start our position at this value number 2, and if we just take like first jump to reach to this value number 3. Okay, so currently the number of jumps we have taken is 1. Now from this value number 3, if we take another jump of the size 3, basically we would be able to reach to the end position, and in total we are only taking 2 jumps to reach to the end. So basically we need to return 2 as the answer in this case. If we try to understand the second examples, things are a little bit different. So in this case we can only take 1 jump. So okay, so currently the number of jumps we have taken is 1. Now from this 1 we need to take one more jump to reach to this position. So again the number of jumps we have taken so far is 2. Now from this 2 we have 2 options. Either we can take 1 jump and reach over here, but that is not the most optimal way. Most optimal way is we take a jump of 2 steps and reach to directly to this end point. So basically the answer in this case is going to be 3, that we need minimum 3 jumps to reach to this last position, and in this case we need minimum 2 jumps to reach to this last position. So this is what the problem is asking us to find, and I know it can look tricky, but it's really simple to do it. And let me show you a couple of different approaches to solve this problem. Okay, so the first approach that comes to our mind is a brute force approach, and in the brute force approach basically we are just going to use the simple logic. The logic is that at any single position we will try to see that how many jumps it can take, and try to explore all the possibilities and try to find that how many jumps it takes to reach to the end element, and also have like a minimum variable in mind that whenever we find minimum number of jumps we will keep on adding it over here, and eventually when we compute all the calculations we should have a result. So in this case what we are going to do is that okay, this value is 2. So first we will consider the possibility of just taking 1 jump. So in this case, okay, if we take 1 jump, we reach over here. Again, we have 3 possibilities over here, but we are only going to take 1 jump. So again, we reach over here. Again, this only has 1 possibility. So we reach over here and then we reach to the end. So in this case, we took in total 5 jumps to reach to the end. Now secondly, we are going to take like different things. So first we will take 2 jumps. So we took 2 jumps, and now we take 1 jump every single time and try to see how when we reach to the end, and so on and so forth, we keep on repeating the same process with different combinations. Now just by the explanation you can imagine that how complicated it's gonna make things, because for every single time you will have to calculate different permutations and combinations of sums, and eventually it's gonna lead to very disastrous results. Like if we see time complexity in this case, it's gonna be in the order of n factorial, because for every single element we will have to compute the process for all the other elements, and that is going to be in the order of big O of n factorial, which is really bad. So we will have to find a better solution, and the better solution is actually quite simple. So let me just directly go to the optimal solution. And now for the optimal solution, we are actually going to use a very interesting concept called greedy concept, and basically we are going to try to make the biggest jump possible every single time and try to see that where does that leads us. Now being greedy is not good in real life, but in computer science it is like the must thing, so you have to do it. Now for the greedy approach, we are actually going to keep track of 4 different variables. So first variable we are going to keep track of is the index value we are currently at. So let's just name it as index. Again, we will also have to keep track of the number of jumps we have made so far. Also we will need a variable to keep track of current maximum variable that we have been able to reach, or current maximum value we have been able to reach. And also from the current index we will have to keep track of that what is the current end value we can reach at. So there are 4 variables. Let me go over them again. First one is the index value. Second one is the number of jumps we have made so far. These 2 are sensible. Third one is to keep track of that what is the current maximum value we have achieved so far, and we will only update it when we find like a better maximum value. When we go through the example, everything will make more sense. And the current end defines it is in correlation with the index value, that where does the current end lies, and if we are at the index value then we will have to make some changes. So now let's look at the example, and currently let's initially assign the values. So initially the number of jumps are 0, current maximum is also 0, and current end is also 0. Now we start our journey. So first we come up at this first index. So whenever we are at the first index, okay, the index value currently is 0. Now the index value is 0. Now let's just keep on updating these values, right? So currently this has value number 1. So if this has value number 1, which means that this 0th index has the potential to reach maximum at the first index, which means the current maximum value we can achieve is that, okay, this current value is 0. Now over here it says that it has maximum potential to reach index value number 1. So 1 is definitely greater than 0. So because it is greater than 0, we will update the value of current maximum to 1, that okay, this is the maximum value we have been able to achieve. Now the interesting part comes. The current end we were at, the current end was 0 because we were at the 0th position, and also the index value we were at was also 0. So because both of these values were same, which means that in order to get ahead to the next index, which is not the last index, again remember I am repeating, in order to get ahead from the current index, which is not the last index, we will have to update the current end, because currently the current end was also here and the maximum value was also here, but this has the value 1, so we have the ability to go to the next, which means the current end needs to be updated. And whenever both of these are at the same place, that means if we are updating the current end value, we will only update the current end value in the condition when we are making the jump. So again, let's just go back to our analysis. Because the index value and the current end both were same, so because these two values were same, we can define that we need to update their values, which means we are taking a jump. So okay, so we made a jump, so we will do jump plus plus, so currently this value becomes 1. But the thing is, where do we update this current end to? We will always go this current end to the whatever the maximum value we have been able to find so far. So current maximum we found is 1. So again, we are going to include this value number 1 over here. Now let me clean this up a bit. So now we are at index position number 1. So we will update our index value. So our current index value is 1. Now at this position, what is the maximum it can travel? Maximum it can travel 3 points. So 3 is going to be 1 plus 3, so that is 4. So now this is the current maximum we can achieve, that is 4. So we will compare 4 with the current maximum we had. Current maximum is 1, so 4 is definitely greater than 1, which means it is sensible for us to update the current maximum. So current maximum becomes 4. Now we will also have to check that what is the current end. Now current end is still same as the index value because this was the current end, so which means that anyways we will have to make a jump. So because we are making a jump, we will update the value over here. So currently the number of jumps we have made so far is 2, and we will also have to update the value of the current end. So max current end we can reach is position number 4, because we already established that that is where the maximum number of jumps we can take. So okay, we are good up until this point. Now again let's make the changes. So now we are at index number 2. So let's see that what story happens at index number 2. Now index number 2, the maximum we can take jump is 1. So if we take one jump, we reach at index number 3. But the thing is, if we check the current max is already 4, and the maximum we can reach is 3. So 3 is actually less than 4. So in this case we don't need to update the current max. Okay, awesome, we are not updating the current max. And now we check, okay, current end is 4 and the index value is 2. So these two are not same. Because these two are not same, we don't need to update the current end or the number of jumps that we are taking. Now okay, now our index value keeps on updating because we are checking this for every single index value. So now we are at position number 3. So now at position number 3 we have maximum 3 possibilities, right? So if we go to 3 steps, we reach to the index number 6. So our current maximum will become 6 because definitely 6 is greater than 4. Now we updated our current maximum. Now we also need to check few other things. Okay, so current end and index value, these two are not same, so we are not going to do any changes for now. So now our index value becomes 4. So let's update this. Okay, so this becomes 4. Now we are at this 4th position. This only has possibility of 1, so this will reach to the maximum of 5, but 5 is actually less than 6. So in this case we will not update the current maximum. Now in this case the index value and current end is both of them are same. So because both of them are same, we will have to do the update. So now when we do the update, okay, we are going to mark the current end as 6 because that is what the current maximum we have been able to achieve, and also the number of jumps we are going to take is going to become 3. Okay, now again we keep on repeating the same process. So again our index value becomes 5. Now because with the 5 index value, the maximum we can take is 1, so that is going to lead up to 6, but we already have current maximum at 6, so we don't need to do anything. And these two values are not same, so we are not going to do anything. Now the index value is at position number 6. Now at position number 6 we are actually able to reach to the end with just a single jump. So we are going to do that. Okay, now we reach to the end of this jump, but the thing is we are just going to, for the sake of simplicity, go ahead with this calculation. So the current maximum we have been able to achieve is going to be 7. That is the end. Now current end and the index value, both of these are same. So because both of these are same, we will have to update our number of jumps that we need to take, and also we need to update the current end. So current end in this case is going to be 7, and we are going to check that if the current end reaches to the last position or the size of the array, that means that is the answer, and we can break out of the loop, and whatever the answer we have been able to find, we can simply return this. So in this case, for this example, the answer is going to be 4, that we can return simply. And this is the most beautiful approach of the greedy solution that I have seen so far. Now if we see time and space complexity, in this case the time complexity is so good because we are only going through every single values and calculating, keeping track of 4 different variables. So time complexity is actually going to be big O of n. So notice that from big O of n factorial we were able to bring it down to big O of n, and all due to the greedy approach that we took. If we see space complexity, in this case the space complexity is actually going to be big O of 1 or constant space. Why? Because we are not using anything else apart from like these 4 values. So that is also a wonderful news. Okay, so let's initialize 3 variables that we need. That is going to be jump, current end, and current maximum, and initially all the values are going to be 0. Now notice that I am not using the index value over here, and that is because we can actually use it from our loop directly. Now let's run a for loop to iterate over the given input array. So now every single time we will check that what is the current maximum we have been able to achieve. So we are basically going to compare the maximum value amongst the existing current maximum value or the value of I plus whatever the value of nums of I for that particular I is, and whichever is maximum we are going to put it in the current maximum. Now we are also going to check one very critical condition, that if the given I is actually equal to the current end we are at. If that is the case, which means we will have to update the value of the jump. So we will do jump plus plus, and we will also have to update the value of the current end. So current end is in this case going to become the current maximum that we have been able to achieve. And believe it or not, but this concludes the whole solution. After we get out of the loop, we can simply return the jump that we have been able to find, and this should be it. Let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And if we submit it, this is beating like almost 99.99% of the solutions in terms of time complexity, and in terms of space complexity, this is also very efficient. So this is a very good solution. And if you see, we are just only using a single loop and just like few lines of code to solve this problem. And I would be posting this in the comments so you can check it out from there. Thank you. So the LeetCode problem we are going to solve today is called partition labels, and we can see that this one is a pretty popular LeetCode problem. Basically, we are given a string that we want to partition into as many parts as possible so that every single letter in each of the partition appears at most at one and not in any other partition. Now note that the partition is done such that after concatenating all the parts in order, the resulting string would be string s. So we cannot just partition randomly from the middle of the string. It has to be sequential. Now let's try to understand it with some examples. Let's say that we are given a scenario like this. Now we want to create maximum partition where every single character only appears in just one partition. So in this case, we can create a partition with this a b a, because remember a appears over here and a appears over here, so they both has to be in the same partition. And then we can create one more partition called d, and notice that if we combine this a b a d, then we would get the resulting string s. Same way for this one, we can create a partition a because that would fulfill that all the characters of a are present. Then we can create a partition called b c d b because b is present over here and here, so it has to be part of the same partition. Now for this third one, we can create a partition aa, we can also create a partition cc, and then we would be creating an individual partition called b, and then there would be a partition called d, and this is what we need to return. So basically in the answer, we don't need to return something like this, the exact partitions, but we only need to return the size of those partitions. So for this example, we would return answer such as 2 and then 2 and then 1 and 1. So these are going to be the sizes. Now the brute force solution is actually quite straightforward. We simply take a character, we iterate over every single remaining values, we see that what is the last point where the character occurs, and then tries to create a partition of that size, and we keep on repeating the same process again and again for every single remaining characters, and so on and so forth. Eventually we would get all the necessary partitions. But the thing is, this is not the most optimal approach, and we can see that this one would run in big O of n square time, so we can do something better. And let's try to find an easy and simplest solution that we can derive from originally brainstorming our brute force approach, and that is to use the greedy way to solve this problem. We are going to be very efficient in picking and choosing how we are going to go forward by selecting the partition. Now the first rule to select any particular partition is to identify that for any particular character, the starting value doesn't matter, but what is going to be the last occurrence for that particular character matters the most. Because once we identify that a character is part of any partition, then we will have to figure out that what is going to be the last place this character is going to be placed at. That is number one thing. Second thing is, apart from being like finding the last position, we would also have to figure out that this partition makes sense if all the characters present in this particular partition has the last point either being this value or before that. I repeat that this can only be a partition if every single unique character that there are present, their last point or the last occurrence would either be less than the index value that we are currently at. So based on using these two values and some additional variables like the partition end time and the partition starting variable, we can actually solve this problem very easily and very efficiently. So let's first identify our first approach, that is to find the last occurrence for every single unique character. So let's say that for A, the last occurrence is going to be index number 2. For B, the last occurrence is going to be index position number 1. Okay, so now we have our list of last occurrences for every single character. After that, we can start iterating over any particular given character in this simple fashion in this given string, and all we will have to compare is that what is going to be the last occurrence compared to its current ith position, and whichever is going to be the greater value, we are going to put it as part of our partition end, because that has to be the partition end, and whenever we find a greater value, we would update the partition end that we are currently at. On top of it, if we are at a position where the given ith value is equal to the partition end, which means we found out a correct partition, so no other character exists that has a greater last occurrence compared to our current value, and we can mark it as a partition. So we can just add it to our result list. So let's say that we are also creating a result list to store all the results. Okay, and let's just follow our approach. So first we identified value number A. So for value number A, the last occurrence is located at position number 2. So the partition end has to be at least value 2. So we'll mark it over here. Okay, and then the partition start initially is going to be 0. Then we are going to iterate over value number B. What is the partition end? Partition end is 1. 1 is lesser than value number 2. So which means we don't need to update the partition end. Next current ith value we are at is value number A, that is located at position number 2. So in this case, because I is equal to 2 and the partition end is also going to be 2, we can actually mark these values inside the result. So currently in the result we are going to have 3 characters, so that we can determine by finding out position start minus position end minus position start plus 1. We'll have to add plus 1 because we are starting with a 0 index. So in this case, first result is going to be value number 3. After that, we are going to update the position start value to the partition 3 number 3, and we are going to reset the value of partition end. Okay, so currently the partition end would be dependent on this particular value C. Okay, so C, for the current C value, the last occurrence is 6 and previous value was 2, but 6 is greater, so we are going to mark 6 as the current partition end. Now for this D, the partition end is going to be 4. So 4 is lesser than 6, so we don't need to do anything over here. Same way 5 is lesser than 6, so we don't need to do anything over here. Now we are at I is equal to 6 and current partition end ends at 6 as well. So in this case, once again we are going to do partition end minus partition start plus 1. So we will have 4 characters in this second partition as well, which are these 4 characters. Now we are at value, now the new partition end is going to be value number 7. Okay, so we mark partition value number 7, and lucky for us, the value we are iterating over for Y is also valued at value number 7. And by the way, the partition start would also be updated to value number 7. So since we found I is equal to 7 and the partition ending position is also 7, so we can mark this as a new partition, and this is only going to contain one element, and same way this is also going to contain one more element, and we can mark it as the answer. And this is the whole solution basically. Let's do a quick recap. First, we created an array that is going to store the last occurrences of every single character. Once we have that, then we can simply go over all of these characters one by one, comparing with the last occurrence, the current position end date and position start value, and we can maintain a result array. And if you see the coding solution, this would become much more sense that how does all of this operates. Now if we calculate the time and space complexity, in this case the time complexity is going to be big O of n, because we will have to iterate over the given input string couple of times, but overall it's just a linear update or the linear traversal. And the space complexity is also going to be big O of n, or this can be big O of 1 depending on how you perceive it, because if we are only talking about the lowercase English letters, then there are only 26 possibilities, and we can use a constant amount of space to solve this problem. So you can debate this with your interviewer that and how they wants to perceive it, but basically both the approaches would be correct. So the coding solution is going to be quite straightforward. First, we are going to check that what is the last occurrence of every single character. And since there are only 26 characters that could be in string s, we can use a simple array instead of using a hash map. We can iterate over every single characters and then just mark their position with the appropriate ith position and just store it in our array called last occurrence. Step 2 is to iterate through the string and determine the partition. For that, we will need to have a variable to store the answer, and we are going to initialize our array list called result. We also need a couple of variables to keep track of the partition end and partition start pointers. So once we have everything set, we are simply going to iterate over the given integer, and we are going to mark the current partition end as the maximum value between the current partition end that we have been able to find and the maximum value of the last occurrence of the current character we are at. Then if at any given point we identify that the given I is actually equal to partition end, then we can simply find we have simply found a partition where there does not exist any more characters further than that point. So we can add that value to the result and then we can start working with our next partition. So we can just update the value of the partition start and then we can keep on repeating the same process, and in the end we can simply return our result array list. So let's try to run this code. So the solution is working as expected. Let's submit this code. And our code beats 91% of all the other solutions, which is excellent. And I would be posting this in the comments, so you can go and check it out from there. Thank you.